All right, so hi, I'm Stefan, and I will talk to you today about the builder pattern and type state programming. And before I start, maybe let me look real quick. Um, before I start, I want to ask you if you recognize this image. It's called Swans. It's from 1956. It's from MC Escher, who is a very known artist, and I love his name or their name because I guess MC are the initials, but I always think of a techno club's master of ceremony when I read this name. So this image, those swans flying in a pattern, also produced on some sort of pattern, is the cover image of the book called Design Patterns: Elements of Reusable Object-Oriented Software by the eponymous Gang of Four. So it's right here. I hope you can see it. And this book is now almost 30 years old. So it has been published for the first time in 1994. It has possibly sold over 500,000 copies because it has really defined how people think of object-oriented programming. Short disclaimer, I learned about object-oriented programming, of course, in university. I have done my fair share of object-oriented programming in the past. I wouldn't tell for myself that I'm an expert in object-oriented programming, but this is all part of this talk because I decided to look at traditional object-oriented programming and see how it holds up in Rust. And those design patterns, this design patterns book defined 23 classic software design patterns with examples in C++ and Smalltalk. And university teachers all over the globe rejoiced because they finally have enough to put on their slides for their curriculum. This is where I learned it. So I learned it at the Linz University, Software Engineering 2, Object-Oriented Programming, and we did all of them in detail, but in a Java context though. The book splits up design patterns in 3 categories. So first, there are creational design patterns. They center around the creation of objects rather than instantiating objects directly. There are structural design patterns. They are concerned about class and object composition. And last but not least, there are behavioral design patterns, which define communication between objects. There's one behavioral design pattern that you should know when you're developing Rust, which is the iterator. So iterator is a classical design pattern, and here you can see how they hold up in Rust. It's also worth noting that the Gang of Four, the 4 authors, Erich Gamma, Richard Helm, Ralph Johnson, and John Lycides, I hope I didn't butcher his name, that they claim that they have not invented design patterns, that they are not a new concept, and they were present in software development for ages, but they were the first ones to collect them, to talk about them, to give them names, so people have a common vocabulary for discussing design patterns. And this is why this book is also so impactful, in my opinion, because not only has it described lots of common things in software development, but people were able to talk about it. And I guess this is why, to this day, this book is one of those which is still recommended, even though, it's the way it's written is I guess you wouldn't write a book like this today, but you can still get a lot out of it. And again, I tried to see how do they hold up in a modern day programming language like Rust. This is a little side project of mine, which I call Gamma's Radiation. Gamma because of Erich Gamma, one of the authors of the book, and the radiation, like, okay, if his ideas radiate to this time, how far do they radiate? So it's a little play on words. And how can those patterns be developed in Rust? You know that Rust has many influences from other programming languages like C++, also influences from other object-oriented programming languages as well. And the Rust book, this one here, I have it here as well, the Rust programming language, which is the paper copy of the one book that you find online, also discusses object-oriented programming. And the funny thing is, it discusses it with a quote from the Design Patterns book. So this is now a quoteception, because this quote here is quoted from the Rust programming language, which quotes it from the Design Patterns book in a talk about design patterns. And it says that this book, that object-oriented programs are made up of objects, yes, okay, and an object packages both data and the procedures that can operate on that data. And the procedures are typically called methods or operations. And well, we have that in Rust. If you boil it down, if you boil down object-oriented programming to that, we have structs and enums and we have impl blocks. So yeah, with that, we have some way of object orientation. It might be a little bit different than you know it from, well, languages like Java, because Rust lacks inheritance, and inheritance is a fundamental concept in Java. And you also, if you think about implementing objects against an interface, yeah, you can do that with traits, but you also need to define the relationship of a trait, like to memory. Like, is it just some marker for monomorphizations over traits through generics, or are you using trait objects, which is a fundamentally different thing and two fundamentally different programming styles. So yeah, we have object orientation, which means it's good to revisit those old patterns of object-oriented programming. And one pattern that I decided to start with, well, next to the iterator pattern, obviously, is the builder pattern, because this is one pattern that I constantly stumbled upon. So I've seen that in libraries, I've seen that in the standard library, and I've implemented a couple of builders on my own as well. It's a creational pattern, and if you do it right, it's also a recreational pattern. And it's in chapter 3 of the book, the first chapter of the design patterns catalog, and it's the second pattern already. So it's pretty early in the book. And the builder pattern is for object creation. It's a creational pattern, and it says that you should use it when the algorithm for creating a complex object should be independent of the parts that make up the object and how they are assembled. And we are going to see a couple of examples for that. And also the construction process must allow different representations for the objects that's constructed. Well, this is, a little bit about polymorphism, and we are not going to touch that. We are only talking about the creation part, about the assembling part. And, since it's a book that it's loved by university, we have class diagrams in there. So this is something where you can fill up your slides like I do right now. And you have a couple of different components in this builder pattern. So first of all, the builder. And the builder is, in this case, an interface. So if I remember correctly from my days back in university, if it's italic, then it's just an abstraction, not a concretization. And the builder specifies an abstract interface for creating parts of a product object. Then here we have a concrete builder, which is an implementation of builder. And it actually constructs and assembles parts of the product by implementing the builder interface. So it defines and keeps track of the representation it creates, but it also provides an interface or a method for retrieving the product. So this is get result in that case. And of course, then you have the product. The product represents the complex object, which is under construction, and the concrete builder builds the product's internal representation and also defines the process by which it is assembled. And last but not least, you have the directory, because everything needs to be an object. Well, what it does, it calls the builder and it assembles parts. So you can say build part that, build part this, yada, yada, yada. Let's see how it works in Rust. So in Rust, you are stumbling upon builder patterns if you look, for example, at Hyper. So Hyper is the crate for doing HTTP requests and responses. You can implement clients with it, servers with it. If you have done anything web-related in Rust, you have used Hyper in one way or another. And Hyper has a wonderful way of constructing requests. And, in terms of a request, it makes a lot of sense. We're going to see why. And this implements the builder pattern. We create the builder by calling request : builder. It gives us an instance of the request builder. And then we have a fluent interface where we can specify different parts of the product, which is a request. We want to get the request out of that. So we have one method to define, well, the method get, post, put, delete, whatever. We can define the URI, we can define a header, and we can add more headers. This is a funny thing about builders, because we can say, well, I don't know how many headers I'm going to have. Why would I need to specify everything upon construction? I have them stored in some variable, in some binding. Let's move them over to the builder. And this is a very flexible part. But in the terms of an HTTP request, this makes a lot of sense. You don't know how many headers you are going to set if you deal with dynamic requests, for example. And also here, the last thing, and this is beautiful, after we have defined everything, we call builder.body, which gives us the product. And the product is the finished HTTP request. And the body method call is the last method call we do. So after that, our object is constructed. And this follows, the pattern of an HTTP request. we are defining method in URI, then we're defining a lot of headers, and the last thing we define is the body. And in theory, up until that point, Hyper could think of, well, maybe we're already sending the first information like get, URI, header, and only when the body is being set, we are closing the request. So you can do a streaming HTTP request, and the way this interface is constructed, it allows you to stream on right away. So this is a nice nuance. I don't know if they do it like that, but the interface would allow it. And yeah, so every step is concrete. And if you think about all the variants an HTTP request can take, and all the variations that you can do, having an interface like that is beautiful. And this leads me to a couple of implications. So first, setting headers can be either very easy or very complicated, but the interface of the builder is prepared for both. And in this example, I did set an HTTP method, but I don't have to, because there's a default HTTP method, which is get. So I don't need to define an HTTP method. So I also have the possibility to default on a couple of values for the properties that I set. And then if you think about having all this complexity, and you think about how Rust defines function interfaces and methods, Rust has no variadic argument lists for functions. Think about println. Println is not a function, it's a macro. Why? Because we have a variadic list of arguments. And you can't set default values for function arguments. So if you use a constructor function like : new, which is, funny enough, a pattern on its own, it wouldn't work as well. And we can see that in this fictional representation of a standard process command. So this is not true. This is something that I put up. A command exists in standard process. It is used to spawn a child process where you can set the command, some arguments, environment variables. You define standard in, standard out, and standard error. And you can have a working directory. And the working directory is, funnily enough, the only thing that is optional. Every other thing, all the other things need to be set. And if I'm doing a standard constructor function where I'm going to set all those values, you see on the right-hand side, this is the new function, and everything is optional except the one thing that I actually need, the one thing that I actually care about. And in my implementation, I either say unwrap or default, or I set it to IO standard in, IO standard out, IO standard error. So I'm setting already a couple of default values. And this constructor function is really, really inflexible. If I look at the usage, look at that. So I have ls.into, then maybe L and A as arguments, and then lots of none. And I don't even know what all those nones mean. So this is something where I say, well, this is a really, really bad interface to use for something like a command, for something that spawns a child process. I mean, I could instantiate it directly, like having the struct open and set command to ls, and then just go for default. If I implement the default trait for command, I can do things like that. But then again, you would need to know a lot about all those properties. And the more complex the object or the instance is, the harder it gets to say, well, just do default. And maybe you really want to know what's behind it, or you want to have a little bit of flexibility. If we look at the actual implementation from standard process, well, they use a builder. Command becomes a builder by say new ls, so list everything with the argument L, with the argument A, and then spawn the process. Cool. That's a one-liner. It's beautiful. And when you read it, you know exactly what it's doing. And if you have something more complex, well, for like the optional working directory, you can say, well, let's do a new command. Let's set a couple of arguments. And then if I have a working directory, well, then please set it and then spawn the command. So again, also from the construction here, again, it becomes obvious what it does, and it's prepared. The interface is prepared for everything. A really, really beautiful interface. And something, I get pretty excited about interfaces like that. If I look at this example from the docs, so I can say either I do something on Windows, it's not PowerShell, I guess it's just command, where I have a couple of arguments, or I call it on Bash, I can decide it in an if condition, whatever. But the beautiful thing here is actually the output. So I'm creating a different kind of object once I call output. I don't call spawn, because spawn just spawns a process, but I don't know anything if I want to get the output or not. And with .output, it executes it and waits until it gets some output, which I can read then afterwards. And I love those kind of things because it's a really, really nice API. I can basically construct my command entirely and then decide if I call output, if I call build or spawn, depending on the context where I am. And this is also a flexibility that I get from a builder pattern. Okay, a little bit more about builder patterns in Rust, because, yeah, well, this is something from the standard library, something from Hyper, but there are lots more builder patterns in Rust. And usually we differentiate between two variations. One variation is a non-consuming builder. And a non-consuming builder is respective to the ownership of the builder structs. So command is a non-consuming builder. If I look at the implementation, this is abbreviated because it has much more, or many more methods. I have a struct command. The input block creates a new command, and with every arg or args that I add, I'm adding something to the list. And if you look at that, both arg and args and also all the other methods there use a mutable reference to itself, which means that the actual instance is going to be changed. And to get a fluent interface, so you can call .arg, it also returns a mutable reference to itself, which means that if you call .arg, if you call .env, it changes the actual instance, and so on and so forth. And this is non-consuming. You don't consume the actual instance. You are changing the instance. And this has a couple of implications. So if I call it, for example, like that, I say let command is command : new with one argument, the return type is not command anymore, it's mutable command. So it's a mutable reference to command. And if I call spawn in the next line, I'm getting an error message because, well, I don't have an owner. So if I call command new .arg, I don't have an owner. The owner is transient. And if I have a borrow later on, it doesn't know what the owner was or what the owner is. And the Rust error message is actually quite nice. Thanks, Esteban, by the way, because it tells you what the problem is. And it also tells you how to solve it. Create the new builder, store it in the binding, and then do all the other changes. So you wouldn't need to assign it then again to binding.arg, assign it to command. But you need to have the first instance. Once you create it with new, you need to store it in a binding to continue with it. And of course, you can still do one-liners. So one-liners are still totally fine. On the other hand, you have consuming builders. And this is also an example from standard thread builder. So you can create a new builder, a new thread via this builder, where you set the name, an optional name, and can set the stack size. But if you look at the interface, this is also abbreviated again to fit on a slide. You see that they take a mutable owned struct. So not a mutable reference, but an owned struct, and also return an owned struct, which means that if you are changing methods within your control flow, you need to reassign to a new binding after each method call. One-liners or chained methods still work as well, but if I would call here thread.stackSize without an assignment, thread would drop. So it would not change the actual instance. It would produce a new instance, and the original instance would be dropped. So yeah, one-liners to an extent still work, and those are the two different kinds. Usually, the Rust style guide says that non-consuming builders are preferred, and you really need to have a reason for consuming builders. So, and this leads me to the second half of my talk, Typestate programming. We now have seen what the builder actually is, and now I want to play a little bit with interfaces. Builders have an actual use cases in Rust. We've seen that good use cases has that. But I want to know if it's easier or if I can steer in some way how my products are constructed. And it should be simple to my users, and it should be elegant, and it should be fun. And what I want to create is, again, it's always my example. Maybe I'm biased here, but I want to create a serverless platform. And this serverless platform creates execution environments where you have a worker or worker process that contains the workload, the one thing that you want to execute, some allocated memory, and a flag if the worker should be kept alive after execution or should be terminated. So, this is the typical cold start in serverless where you say, well, I boot something up, and then please keep the instance because I want to send the same workload over and over again, or I want to use the same parameters. And, to execute everything, to spawn a new worker or to build a new worker, you need to have all properties set. You need the workload, you need the mem size, and you need keep alive. However, only mem size and keep alive can be pre-filled with defaults. You have some default settings and you can change them later on, whatever. But they are defaults, the workload isn't. And the workload might come from an external source, so you don't know when constructing the instance if you already have a workload ready, or if the workload comes from some stream or some request or whatever. And this nuance is mirrored in the WorkerBuilder. If you look at the WorkerBuilder, it has the same properties as the worker, but it contains an option of a string. So the workload is not yet defined. Either we have a workload or we have no workload. And this is, by the way, also a great usage of a worker because, you are assembling parts, you're constructing things with a builder. And if you don't know about certain things yet, well, then you have an undefined value, or you have a nullish value in other programming languages. In Rust, you have the option to a value. And you can make sure that only if the workload is set, that you have an actual worker at hand that has everything it needs. So the builder is a great way to get rid of those optionals if you don't need them. So yeah, a little bit of a different API, and that has some reason. So now let's implement a very rough implementation of a worker builder. So first of all, we have the worker builder up here. We're creating a constructor function. It has no arguments. So we say workload. There's no workload. We don't have one defined yet. We create the memory size. This is, in megabyte, I guess, 128 megabytes. And we don't want to keep it alive. So the worker is terminated after execution. And then we have the workload method. So this is where we set the workload method. It's a mutable reference to myself, which means it's a non-consuming builder. And workload impels into string, which means that anything that can be converted into a string, I take it. This is a beautiful way of monomorphization, beautiful way of working with generics, where I just say, well, give me whatever you have. Can be a string slice, can be an owned string, can be anything that implements toString or display. Doesn't matter. As long as you can be transformed into a string, I'll take it. And then I said, well, I set the workload to this workload. I call workload.into to go from what it had to an actual string, and it return myself. This is how I get this chainable interface. I dropped the methods for memsize and keep alive. They're pretty easy. We're going to see them later anyway. Okay, so this is how I set my workload. And then I have here the build function where I say, well, I create the worker and it has the workload. I call unwrap because, hey, I'm sure that workload has been set. I transfer memsize, I transfer keep alive and have this worker. And actually, this should be just self or a consuming method, because after this step, I want to consume the worker builder, so the worker builder can't be reused again. After the worker builder terminates, I want to be done with it. So this is an error in my slides. I'm very sorry about that. But here's one problem. So I have this scared emoji right next to it, because, hey, I'm calling unwrap here. This is an unsafe operation. This might panic. If I didn't set workload, everything might go boom. And I want to avoid that. And I want to avoid that. Well, I have a couple of possibilities there. First, I could just say, well, you're not getting a worker. You're getting the result of a worker, or maybe a construction error. Result types work beautiful in that. And you have transformation methods from an option to an error and back. Would be a beautiful way to develop. But, well, actually, why would I even allow to call build if I don't have a workload set? And I can implement that stuff. I can implement that through Typestate. Let's see how I do it. First, I change the worker builder interface. So I say the worker builder now doesn't have a workload, which is an option of string, but it has a generic parameter. It has a generic parameter where I have not decided yet what the workload should be. And then I'm going to implement the generic worker builder. Those are all the methods which don't care about the state of my workload, because the workload has a state. Either it's here already or it isn't. But those methods for memsize and keep alive, they don't care about the state of the workload. So I can implement that for the generic version of worker builder. And this is what I do here. So it just set as you have implemented that. And again, it takes a mutable reference, returns a mutable reference. So it's a non-consuming builder. But now I start with the case, what if I don't have a workload yet? And I define a struct no workload. Look at that. It's an empty struct. It has no fields. It's just here to say, well, this is one thing I want to care about. And then I implement WorkerBuilder for this particular struct. So no generics anymore, just for this particular struct. And here, in this particular implementation for WorkerBuilder of no workload, I have the constructor function. And the constructor function says new, it returns workload, which is no workload. It fits because, hey, that's my parameter here, that's okay. The mem size and the keep alive. Fine, that's great. And I already defined mem size, I already defined keep alive. So now I need to define workload. And it takes again a workload implement to string, but look at that now. I'm not returning self or changed something in my parameters. I'm returning a new WorkerBuilder. I'm returning a new WorkerBuilder where I set the workload into, well, this particular string, where I set the mem size to self mem size, keep alive to self keep alive. I'm moving those fields over to the new WorkerBuilder. And if you look at the function signature, if you look at the return type, I'm now not returning self. I'm returning a WorkerBuilder string. So I'm having the same struct, the same type, but I have a different state of my generic type. So I'm moving from no workload to string. And you can really think about it like a state machine. So you start at no workload, and when you call workload, you're moving to a different state. So let's implement the rest. Let's implement WorkerBuilder of string. Here I have the build method. And again, sorry, this is wrong. This shouldn't be an ampersand mute. This should be just self. And this one, since now I'm 100% sure that I have everything that I need, that I have a workload, I can simply construct a worker with the workload, with mem size and keep alive, and return that. And yeah, that's the last state. And the beautiful thing about that, workload has a different state. Workload has a state where it starts, which is no workload, and then it has a state when it ends, which is I'm having a workload of type string. And those are two bookends of the construction process. So this is where you start in the builder pattern, you start creating your builder, and then you are done with the building process and you're getting an actual object or an actual instance of your struct. And those two bookends are always there in a builder pattern. And the one thing in the middle is variable. This is the one thing where something changes. And those two bookends are separated by state by the different implementation blocks. So it becomes totally obvious which state should be the start, which one should be the end. And you know what? I do think I have some time left. Let me quickly switch my screen to. There we go. Yeah. So actually, now I just had a talk and I'm doing some slides. Now it's getting really interesting because I'm doing NeoVim and I haven't done it yet. Oh, sorry, I should add it to the stream. Damn it. So it's going to be interesting. I hope I don't. I'm not stumbling over myself here. But here I've implemented everything you've just seen. Here I have the worker, I have the struct no workload, I have this WorkerBuilder of W. I have the implementation for the no workload state. And I'm having here the WorkerBuilder of string, where I'm actually getting the build method. So yeah, here I've also changed something. So here I've also changed it to a consuming call because I'm getting a new struct. So this is okay. This works like intended. And here I'm having mem size and keep alive. So there you go. And now let's try to implement it or to work with it. So I'm having my worker, and I say WorkerBuilder. Yeah, okay, new editor, colon, new, there it is, works fantastic. And if I look at it, I'm getting a WorkerBuilder of no workload. So the inlay hints from Rust Analyzer already tell me that I'm having no workload. And I can do things like, whoop. Working with a new editor for the first time. It's ridiculous. There we go. So I can do things like set mem size and set or keep alive to true, and here setting mem size to 256 times this one here, and if I save it, there you go. And so I'm still having, you don't see it that well. Let's add let's add keep alive again. So Rust analyzer formats, something nice. There you go. You see that I'm having here a WorkerBuilder of no workload still. So nothing changes here. It's still a WorkerBuilder of no workload. But if I'm going to change this to build, look at that. I'm also getting the notice, well, no method name build found to struct WorkerBuilder. So it's not there. It's not within the implementation that I have here. And if I do cargo build, it also tells me method not found in WorkerBuilder no workload, but the method was found for WorkerBuilder string. So again, thanks Esteban, those are great error messages that help me with my case. So I go to this line and say, well, now I'm setting a workload. And I'm setting it to an empty string. And look at that. Now it changes from WorkerBuilder no workload to WorkerBuilder string. And now I'm also having the build method available. And now I'm getting a worker. So this is what I get out of that. And I still can work with those generic methods. I still can say, well, let's have mem size and set it to something entirely different. Or let's call keep alive and change it to false. So I'm still having those methods that come from the generic implementation. They are still there because they're generic over all possible states. But the moment I add a workload, I'm moving state from the concretization of no workload to the concretization of string. And this is how I can use Typestate programming to make sure my APIs are good, to make sure that when I develop something, that my users and everybody who uses my APIs are not doing anything wrong. And I don't have any weird states where I need to take care about results when the only thing that can happen is to have a workload in the end. So if my API tells me that I need to have a workload, then I need this pattern or this way of constructing objects is really, really nice and helps me a lot in the way I work. Okay, back to my slides. Just 1 second. And boom, boom, boom. Here I go. So okay, you should see my slides again. There you go. Okay, I showed it. That's fine. Little summary. So how far went Gamma's radiation? Yet I guess the builder pattern holds up really well. In fact, I think it's perfectly suited for us. So it shows with a lot of examples that we've already seen in Hyper, in the standard library. And if you have situations where you're constructing a complex object that may react to certain things in your program, then well, it's really good to use a builder pattern if you want to construct something. The pros are it's suitable for one-liners, so for easy construction, but also for complex construction. It prevents proliferation of constructors, which means, well, what if your constructor takes in I don't know how many function arguments or methods function arguments. How often do you need to set an option, even though you shouldn't? If the constructor gets more complex than instantiating it directly, then why not using then why don't you use a builder directly? It hides the complexity of the product, and with Typestate, it can add a fantastic and type-safe API. The cons are, well, constructor functions or direct construction are simpler in design. They might be more accessible in the beginning, but well, if you have simple objects or simple structs, then a builder pattern is obviously overkill. And with that, I'm at the end of my talk, and I'm open for all the questions and say thank you very much.